Okay, so welcome to the third and last lecture. Let me see, am I sharing or am I not sharing? I think I am not sharing. Okay, so here. Okay, so today I'm going to talk about canonical groupoids associated to an inverse semigroup and results characterization of simplicity of the Steinberg algebra. Here are the references. Just one small comment. In my last lecture, I mentioned that Steinberg algebras appear simultaneously in a paper by Steinberg, which you can see there, and also in a paper by Lisa Orloff-Clark and co-authors, which is the one right above, a groupoid generalization of Leavitt path algebras, which I will cite today. Okay, so yeah, screen sharing stopped. Okay. Okay, so hopefully I will. The camera director will show me. Okay, so universal groupoid of an inverse semigroup. Okay, so let S be an inverse semigroup, and sitting inside S, as before, we write script E for the subset of all idempotent elements, which we know conform an inverse subsemigroup, which is commutative. So a semi-character is a non-zero pointed semigroup homomorphism phi from E to 0, 1. So 0, 1 is regarded as an inverse semigroup with a product. Okay? So what this means, therefore, is that phi is not identically 0, that phi of 0 is 0, and that, well, phi of PQ is phi P, phi Q. Okay? So we have the set. This is the set of all functions from E to 0, 1. Sitting inside here is the set of it's the set of all homomorphisms. And inside here is the set of homomorphisms, which in addition are non-trivial. These are the semi-characters. Okay. Now, one can equip this with the product topology. This is the product of E copies of 0, 1, 0, 1 with the discrete topology. And this is, by Tikhonov theorem again, this is compact. And in this topology, net converges to a function phi if and only if for every p in E there exists a lambda sub p, such that if lambda is greater than lambda p, then phi lambda of p is phi p. So pointwise, so for a sequence, for a net to converge to a function, it needs to be equal to the function from starting from some lambda, which depends on the point p. Okay, it follows using this that the subset of homomorphisms is closed and therefore compact. And this is h minus the constant function 0. So it is open in this compact subset. And therefore it is locally compact and Hausdorff. It need not be closed. Why? Because it might be that none of the phi lambdas, so all of the phi lambdas live here. None of them is equal to the zero constant. However, it might be that for every p there is some lambda greater or equal than lambda p, such that this is 0. Okay? So this need not be closed, not closed in general. So in general, it is locally compact and Hausdorff. Moreover, it is generalized Boolean. So it has a basis of compact opens. So say for p in E times, which is E minus 0, we consider dp the set of all phi in E hat, such that phi of p is 1. Okay? So notice that if phi of pi is 1, then it is not constantly 0. So this is the same as the phi in H, such that phi of p is 1. And what is this? This is H intersection the product for Q different from P of 0, 1 times 1. So here I am regarding 0, 1 to the E as the product of E copies of 0, 1. Right? So I take all those copies except the piece 1, and in the piece 1 I put just the singleton 1. The sets of this form are open and closed in the topology of the power set 0, 1 to the E. And so when I intersect them with H, I get a Klopen subset. This is Klopen in H. And since the power set was compact and H is closed, so it is also compact, then this one is compact. and open, compact, open. Right. And fact, the DPs unique form a basis. This is easy because, I mean, the basis for the product topology are the sets of this form and with a 0 here. Right? Okay. So, okay, so here we have a generalized Boolean space, E hat, and we want now to give an action of the semigroup S, and the transformation groupoid will be, of that action, will be the universal groupoid of the semigroup. Now, first, we let S act on E via S acting on P is SP S star. Okay, this is not, I haven't forgotten the hat. The action on E hat will come later, okay? So this action satisfies two things. So first of all, ST times P is the same as S times T times P. And second, if I do SP times SQ, where P and Q are two idempotents, then what is this? This is SP S star S Q S star. Now, as I said several times, idempotents in an inverse semigroup commute. So I can take this one and put it here. So I get S star S PQ S star. But by definition, S star S is S. And this is S PQ. Okay? Right. Now I will use this action to define an action of S on S hat. As follows. Okay. So theta S will go from ds star S to ds S star, where recall we defined dp as a set of all semi-characters that are non-zero on P, right? Okay. So theta S will go from here to here, and what will it do? Well, first of all, we will abuse notation and write S of phi for theta of S of phi. And S of phi applied to P, where P lives here, where phi lives here, sorry, will be phi of S star dot P. Okay, so phi of S star PS. The fact that I've taken the inverse of S to define the action of S on functions, so I have some structure like a group or an inverse semigroup that acts on some set. And I have functions on that set. Then to get a left action, I need to take the left the left action of the inverse and then apply the function. This gives me a left action on the. So it follows from this that well, whatever has to happen happens, namely this holds, and this follows from the properties we just mentioned above, and it also is an easy calculation to show that if phi is in D S star S, then S phi is in D S S star. Okay, all this is exercise. Right. So this is the action, and when one checks that this is continuous and everything, and so we can form the transformation groupoid. And the transformation groupoid of this action is what we call the universal groupoid. So why is it universal? Well, say you have an action of S on some space X. Okay? Right. Then you can go from X to E hat as follows. I don't recall what name I had given to this. Yeah, well, okay. So you may send X to phi X. And what does phi X do? Phi X evaluated on P is a characteristic function of dP evaluated at X. So there are several dPs. dP is say this action is rho. Okay? So if one has an S here, then the action rho S goes from D rho S to codomain rho S, right? So this is, let me put it, this is D of rho P. Okay? So it turns out that this is a continuous and S equivariant, meaning that if you have something that is in the domain of S, then its image here is also in the domain of S, and that the action is the action goes to the action. Therefore, you get a map, a groupoid homomorphism from here to here. And if you have a function from here to k, say that is in the Steinberg algebra of the universal groupoid, then composing with this, you get a function that happens to be in the Steinberg algebra of this groupoid, and the map that associates phi to phi bar is the canonical map that I mentioned in the last lecture. Okay, so the canonical map coming from the last lecture is induced by a group of homomorphism that stems out of the universal property of the universal groupoid. All right. And therefore, well, as with all universal objects, the canonical map, in the case when X is E hat, and the action is the action I just mentioned, is the identity, right? And so the canonical map that I talked about last time happens to be an isomorphism in that case. So theorem which this you can find, well, so the canonical map came from the semigroup algebra, right? And so when I said it is induced by, so the canonical map is induced by that, blah, 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 what I meant was, I mean, the canonical map, the map induced by this groupoid homomorphism goes from the Steinberg algebra of the universal groupoid to the Steinberg algebra of the other groupoid, right? But in the canonical map I mentioned the other time, the source was the semigroup algebra, not the Steinberg algebra of the universal groupoid, which we hadn't still defined. What Steinberg says is that the canonical map, the canonical algebra homomorphism is an isomorphism. Okay? Okay. Yeah.
Are not non-zero, are not zero. Where is that coming from?
That's the definition. So, for example, the zero. So he asked. So this doesn't show in the Zoom, but I was asked why do I require that semi-characters do not vanish, are not canonical, not constantly zero? Well, that's the definition. Was my answer. Okay, so for example, zero is a pointed semigroup, the semigroup consisting of just a zero element. Is an inverse semigroup, pointed, whatever. And well, it's its own idempotent semigroup. And then you can take its hat, and what you get is the empty set. Okay. So there is another way of looking at semi-characters. After all, semi-characters are functions from E to 0, 1, and functions that can take only values 0 or 1 are characteristic, also known as characteristic functions of subsets of the set. So we'll go into that interpretation in a second. So first, define for P and Q in E. We say that P is greater or equal than Q if PQ is Q. Then automatically QP will also be Q since P and Q commute, because E is commuted, right? All right, so for example, in the case of the semigroup associated to a graph, the idempotents are the things of the form alpha alpha star, where alpha is a path, union 0. Okay? And then alpha alpha star is bigger or equal than beta beta star if and only if beta is of the form alpha beta 1. So so the idempotent corresponding to the path alpha is bigger or equal than the idempotent corresponding to the path beta if and only if alpha is the first segment of beta. So if beta is equal to alpha, this is just a vertex, okay? Otherwise, there might be something more. So in this case, we say that the path alpha is greater than beta, and then we get an ordered isomorphism between this with 0 added, with the empty set added, and this order. So this is a poset is iso. Okay. So what kind of sets are what kind of subsets of E are such that the characteristic function is a semi-character? So then phi is in a hat implies, as we just said, that phi is the characteristic function of f, and the fact that phi is a semi-character if and only if two things happen. One is that, well, 0 is not in F because phi is supposed to be pointed, so 0 has to go to 0, not to 1. Right. And, well, second, F is not empty. So that is not constantly 0. And third, PQ is in F if and only if P is in F and Q is in F. This is what it means that phi of PQ is 1 if and only if phi of P is 1 and phi of Q is 1. Okay? Always taking into account that the complement of phi of P being 1 is phi of P being 0. Now, 3, you can separate it in two conditions, 3.1 and 3.2. 3.1 says that if P is in F and Q is bigger or equal than P, then Q is in F. Right? So here so if Q is bigger or equal than P, then QP is P. Right? So this says P is in F, and then P is in F again, and Q is in F. Okay? And the other implication, we leave it as it is. So P and Q in F imply PQ is in F. So in terms of the order we defined, this says that F is closed by up sets. So if somebody is inside, then all the bigger or equal are inside, and also by so how is this called? The minimum. This, in the terms of the order, PQ is the minimum of P and Q. Okay, so E with this order is a semi-lattice, meaning that it has, even any two elements, it has the minimum, but not necessarily the maximum. If it had a maximum, it will be a lattice. Okay. So in the case when F satisfies this 1, 2, and 3, we say that F is a filter. Now one can consider the set F of all filters this is in bijection with the hat by what we just said. The bijection maps F to the characteristic function of F. And this is ordered by inclusion. These are all subsets. And by Zorn's lemma, for every F, there exists an F prime containing F that is maximal in F. Okay? So an ultrafilter is an F in Fcal that is maximal. Okay, so the action of the semigroup, if you translate it into filters, preserves the inclusion. So at least if a semi-character corresponds to an ultrafilter, then the action will map it to another ultrafilter. Now, ultrafilters form a subset of E hat, but this subset need not be closed in general. And so we take the closure. So a tight character, a semi-character, sorry, is a semi-character that is in the closure of the characters corresponding to ultrafilters. Okay. So let's see. And then we write GT of S or Z tight of S to be the transformation groupoid of the action with respect to the tight character. Okay? Right. So what does this give? So say we have E a graph, and S is SE. Then we have already seen that this is isomorphic as a poset to the paths of E together with the empty path, with the order of paths that we define. Okay, so one can check that F always filters by definition do not contain zero. So they correspond to a path, not to the empty path, right? And then one can check that this is a filter if and only if it is totally ordered. Totally ordered with respect to the path order. So okay. So so say we have a filter which we identify with a set of paths, a filter. Then it's either finite or infinite. 1, 2. In case 1, since filters are closed by, so if a path is in the filter, the non-bigger paths have to lie in the same filter. So if E1, En is in the filter, then E1, E2, En minus 1, up to E1, up to the source of E1, are all in the filter. Right? So if this is finite, then there will exist a path alpha such that F consists of all the betas such that beta is bigger or equal than alpha. Yeah. This is what I said before. Yeah. So this means that alpha is beta alpha 1. So bigger means smaller in size. The length is smaller, but in what sense is it bigger? Well, you imagine the path. You have a dictionary of paths. Then what are you going to put first? The ones that have the less letters, right? So in that sense, beta is bigger. It's first in the dictionary, okay? Okay. And also it corresponds to a bigger idempotent. And then in case 2, you can show that there exists x in xe, which we let me recall are the infinite paths, such that f consists of all the alphas, such that alpha is bigger or equal than x, which again means that x is alpha y for some infinite path y. Okay. So using this, one can check that E site is in bijection with xe, where the filter corresponding, the bigger or equal than x, the alphas bigger or equal than x, go to x. And whereas E hat corresponds to xe hat, which consists of xe union the finite path. Yeah.
This is a consequence of the fact that of these two types, only one of them can be.
Yeah, well, yeah. Sorry, I forgot to say. We are assuming that every vertex emits at least one edge. So, because of this assumption, the only ones that can be maximal of the filters I mentioned are those that correspond to infinite paths. So in that case, xe is compact, so it's closed, and we are in a Hausdorff setting. So this is already closed, so there's no need to take the closure. Right, and then an observation is that if you have a finite path, then this is the same as the path beta, such that alpha. Well, let me see. So this set is open. Each of these is open in here. in here. Right? So these are kind of the isolated points in X hat. Right. And okay, so the algebra of the universal groupoid, according to Steinberg theorem, is K of SE. This is called the cone path algebra. And recall that SE is generated by the E's, the E stars, and the B's. And these E's are in E1, subject to E star F is delta EF times the range of E. So it follows that KSE is also generated by the E's, the E stars, and the B's, subject to the same relation. In the case of the tight groupoid, you get a quotient of this. And you can see that so there is a relation that you have in the case of the tight groupoid that you not, the algebra of the tight groupoid that you do not have in the universal groupoid, namely if you have, say, you have V is a vertex, right? Then ZB is all the x's in XE such that the source of X is V. Okay? Now, all these are all infinite paths. So at least they have length infinite, so they begin with some edge E. So this is the union, the disjoint union, over all the edges E with source B of ZE, where ZE are the infinite paths that begin with E. Therefore, when you take the characteristic function of ZB, you get the sum of the characteristic functions of ZE, where the sum is over all the edges coming out of B. This gives you a relation in the quotient, so LK of E, this is called the Leavitt path algebra. Is AK of Z tight of SE. Then this is the compass algebra divided. So recall that in this we are associating, so E corresponds to the element E of SE, which in turn corresponds to the characteristic function of ZE under the canonical map. Okay, the characteristic function of of EE star ZE. So this gives us a relation, which is that B is the same as the sum of the EE stars, where E comes out of B. And it turns out that these are the only relations. Okay? So this is what you get. In general, tight characters can be defined, I mean, by some property. So are characters verifying some equation. So for example, in this case, what this is telling us is that the type characters have to do with phi of B being the sum of the phi of E star. Okay? But you cannot say in the language of the semigroup, there is no supremum. So you have two elements, there is the supremum of the two is not defined. So it's complicated to explain what in semigroup language, what a semi-character is in terms of equations. This is done in Excel's monograph. And he shows that the set of those characters are precisely the ones that correspond to ultrafilters. Okay? But what I wanted to say is there is an equational viewpoint. And in the, I think, 15 minutes, I think I started 10 past. But I think maybe I can do with less than 15, but well, let me start. Now I want to go over to simplicity of the Steinberg algebra. Okay, so we have G an ample groupoid. And then we call that the cops of G act on the unit space as follows. So if B is a cop, then B defines a homeomorphism from its domain to its codomain, which comes from the fact that the domain and codomain functions, when restricted to be a homeos, so you get this in here. So since there is an action, one can define orbits. The orbit of a unit X, or unit is, I use it as synonym for object, is the usual parlance in groupoid theory. Put OX to be the VX, where X is in the domain of B, and B is a cop. Okay, we say that G is minimal if for every X in G0, the closure of the orbit is the whole of G0. So this is a transitivity condition. So if this holds without the closure, we say that the groupoid is transitive. It acts transitively on its unit space. This is slightly less because we can stick a. So what we're asking is not that the orbits give the whole thing, but that they are all dense. Okay. So another condition that will be needed for the Steinberg algebra to be simple. So here, when I talk about simplicity of algebras, I mean by simple algebra, or a simple ring, I mean one in which the only two-sided ideals are 0 and everything, and they are 2 and distinct. So the 0 ring is not simple because it has just one ideal. I want it to have exactly 2. Okay. Yeah, yeah. But let me wait until the end. So I will say what it means, what the character, I mean, it's a trivial example of a minimal is you take a group G acting on a space X transitively. And then you take the transformation groupoid, yeah. Okay, so next, for given X in Z0, we write Gxx to be all the G's in G, whose domain and codomain coincide with X. So for example, X is in there, and notice that this subset of any two elements of this part of the groupoid can be composed, right? And well, the inverse of a semigroup of a groupoid element in here is also in here. So this is a group, and this is the unit. Okay, so this is a group, and X is the neutral element. Okay. So in honor of the co-host of the Zoom meeting, we call GSO is the union over all units X of the GXX. So since GXX contains X for every X, this contains the whole G0. And this one is open in G, happens to be open in G, and therefore it sits inside the interior of GSO, right? So we say that G is effective if the interior of GSO is precisely G0, if there is nothing else in the interior. Then here is the theorem, which you can find in the article by Clark, Excel, and I think the other one is Pask and Sims and Starling. Theorem 314, like pi. So say K is a field. So it doesn't make sense. So if you have a ring which is a commutative unit, a ring K which is not a field, then you will have ideals, and these ideals will give ideals of the Steinberg algebra. So to consider simplicity questions, we always assume that the ground ring K is a field, and we suppose that G is sample and second countable. This means that it has a countable basis of open subsets. Then AKG is simple if and only if G is minimal, G is effective, and the third condition, the third condition is that for every F in, or every phi in AKG non-zero, the support of phi, which remember we define it as the inverse image of 0, not the closure, the inverse image of 0, interior is non-empty. So by what we saw last time, if G is Hausdorff, then this condition is automatic. So this condition is what, so if G is Hausdorff, if you know that G is Hausdorff, then simplicity is equivalent to the first two conditions. The first two conditions depend only on the groupoid, not on the field K. This one may depend on the field K. So it might be that that the Steinberg algebra over the complex numbers of a groupoid is simple, but over the field of two elements, it is not. So there are examples and have been studied by Steinberg and Shasaks, I think it's the pronunciation. Somebody with somebody from Hungary has a name that I don't know how to pronounce. Okay, so to finish, I want to say how this translates, how these properties translate in the case of Leavitt path algebras. So let E be directed graph as before, which means that E0 and E1 are finite, and S minus 1 B is non-empty for every B in E0. Then a cycle in E is a path E1 n such that R of n is S of E of S of E1, so it's a closed path. And for every I different from J, S of EI differs from S of EJ. So it is a closed path that doesn't go twice over the same, through the same vertex. Okay, so the support of, so call this C. The support of C is the set of the sources of all its edges. Okay. So I need some more notation. So an exit of the cycle C is an edge E such that there exists I such that source E equals source EI, but E is not EI. Yo tengo de falta un minuto para las. Okay. Okay. And we need one more thing. We say that a vertex B connects to my cycle C if it exists a path that comes out of B and lands in the support of C. Okay. So theorem, this is in the book by Abrams, Ara, and Siles Molina, which I abbreviate as LPA for Leavitt path algebras. Theorem 297. It says that LKA is simple if and only if every cycle has an exit, and two, every vertex connects to every cycle. Okay, so we already saw that XE is a Hausdorff. So these two conditions correspond to minimality and effectivity. Okay? And the compass algebra is never simple because it has an ideal by which you have to divide to get a Leavitt path algebra. And well, this is all for today and for the course. I hope you've enjoyed it.